Hello. So now we're going to discuss population growth. So the assumption here will be that this population will focus on the concept that the growth rate is proportional to the population size. Okay, so that's basically what will motivate how to construct a differential equations that is related to this given phrase. Okay. So when they say the growth rate is proportional to the population size, what they mean is that the growth rate basically is what we call dPdt is proportional to the population size. So we have a dp dt equals k times p. So basically, a dp dt is what we call the growth rate, and the p stands for the population side. So k is a constant. So basically, that's what we're saying. The growth rate is proportional to the population because of this equation. So that's the model for this problem. Now, this is what we call a differential equation. So what is the solution of this differential equation? The solution is going to be basically an equation that give us the population per given time. So when you solve that differential equation, which is this is calculus one, so we don't really know how to solve it, but when we solve it, the solution is going to be basically p of t equals p sub 0 times e to the kt. Um, so it's going to be c times e to the kt, but c is basically the initial condition, the initial population, which is a p of 0 with p sub 0. Okay, so when you solve that differential equations, that's what you're going to get. And basically that's the solution to the differential equation. For example, here they said here the world population was 2,560 millions in 1950. And then in 1960, we got the 3,040 millions of people. And they want us to model the population, the world population, in the second half of the 20th century. So here they said they assume that the growth rate is proportional to the population size. They're assuming that the differential equation dp dt equals kp. That's what you want to use. What is the relative growth rate? The relative growth rate is k. Okay, so it's k. Okay, that's the relative growth rate. So then use the model to estimate the world population in 1993, and also to predict the population in the year 2025. Okay, so the solution is this. So first, we're going to assume that at time t equals 0 will represent 1950. That's the beginning year that we're using for this problem, 1950. So we're going to call that year 1950 be t equals 0. Okay, this is the beginning. If that's t equals 0, then at 1950, then 1960 is going to represent t equals 10. Okay. So t equals 10 will represent 1960, because you can take 1960 minus 1950, give you 10. So that's t equals 10. Okay, so now let's just look at the data, for example. So we're going to base our knowledge on dp dt equals k times p. We know the solution to this differential equation is a p equals p sub 0 times e to the P sub 0 will be P of 0 times e to the kt. Okay. P of 0 is the original population. So we're going to just use the number. We're not going to use millions units. It's going to come after million. So whatever we get is going to be the number we're going to get, and then million is just going to be millions, is going to be the units. So when you use, instead of using like 2,560 millions, we're going to just use 2560 as a P of 0. And the P at 10, which means in 1960, we're going to use 3040 in the formula. Okay. So we're going to base our solution on this. This is the solution of this differential equation. So P of 0 is basically the initial population. So which is 2,560 millions. Okay. So we put it here. So we replace P of 0 by 2060 and then e to the kt. But then they also give us P of 10. Okay, so 10 is when P of 10 means the population a year t equals 10. So that means we have this equation P of t equals 2560 times e to the kt. Now from here we're going to plug in t equals 10. So that means on the numerator, on the exponent of e, is going to be k times t, which is k times 10, or we can write this as 10k. But what is P of 10? P of 10 is at 3040. So we have this equation that we're going to use to solve for k. Okay. So k is the relative growth rate. So we're going to solve for k. So this is an exponential equation that you're going to solve for k. The first thing to do is to divide both sides by 2,560. This equation, we divide both sides, and then to bring k down, we have to apply natural log to the equation. So when you apply natural log to the equation, you get 10k equals to natural log of 3040 over 2560. Okay, and then to get k, you divide it by 10. When you use a calculator, you get your relative growth rate, which is 0.017185. Usually, when you write it down, you want to multiply by 100 to get to 1.7% per year. Now we got k. Okay, so then we go back to the equation. We plug in k. So when you use the formula, you use the decimal version of k. Okay, so k is 0.017185. So we plug this into here, into the formula. P of t equals 2560 times e to the k. Now it's none. It's not unknown anymore. So we put k there. Give us this formula. So we're going to use this formula to estimate the population side at in a year 1993. Year 1993 basically means t equals 45. How did you get 45? You take 93 minus 50. Okay, because the original year was 1950. So you get for the t equals 43. So you go to this equation, you plug in 43 for t, then they give you this estimate of the population in the year 1993. It's going to be of 5,360 million people. Similarly, we can estimate the population in 2025, which is P of 75. So again, you go to this equation, you plug in 75 for t, use your calculator to get the population. So in the year 2025, you're going to have this many people, 9,289 million people. Okay, so basically that's the exponential growth problem. Thank you.